Okay, well, here we are for lecture one of this week, and we're going to pick up where we left off in chapter two. Things have been going a little too slowly. We're well behind. Part of it is that just chapter two goes on and on and on forever. So I'm going to try to pick up the pace a little bit. One thing I'm going to try to do is making the videos directly from the lecture notes that I have already written up rather than writing them as I go along, because that will save some time. So hopefully we'll see how that works. If anybody finds themselves getting lost, well, you can have the advantage to doing it on video is that you can always stop the video and back it up a little bit and go over it again. So I'm hoping that this won't be too slow. I will, or I mean that it won't be too fast. In class, I'm going to continue writing the notes on the board as we go along, because I think if you don't have the video and the available or and the ability to back up and go over it again, then pretty much having it all written up ahead of time and just plopping it up on the screen would be presenting stuff to you too fast. But here, because you can review it, I hope that won't be a problem. Anyway, where we left off was we were about to identify or define the idea of the null vector. The null vector is just a vector whose components are all zero. It's something that you get when you multiply a vector by zero. We've seen already that you can multiply a vector by a scalar, and a scalar is essentially just a number. And if you do that, then you end up multiplying all of the magnitudes of the x and y and z components by that scalar. Well, if that scalar happens to be zero, then all of the components end up with zero as their magnitude, and you end up with what's known as the null vector. Also, we should mention the idea of equal vectors. Equal vectors are two vectors that have a difference of zero. So essentially, they have the same magnitude and the same direction. Or in other words, their difference is the null vector. So if zero, that is zero vector or the null vector, is equal to a minus b, and a is the x component of a times the unit vector in the x direction plus the y component of a times the unit vector in the y direction plus the z component of a times the unit vector in the z direction minus b, which is again the magnitude of b in the x direction times the unit vector in the x direction and so on with y and z. Then you could also rewrite this equation as ax minus bx, that is the magnitude of vector a in the x direction minus the magnitude of vector b in the x direction times the unit vector in the x direction. And then you do the same for the y component and the z component. And if a minus b is equal to a null vector, that means that ax minus bx must be zero, and ay minus by must be zero, and az minus bz must be zero. Okay, and I've had a habit so far when I write zero alone of writing the crossbar through it to emphasize that it's a zero. I'm trying to get out of that habit because it looks too much like the angle phi that we've been using for some purposes. So yeah, so I'm just going to try to write it as zero from now on. So you can say that vectors a and b are equal if the magnitudes of their x and y and z components are all the same. Or in other words, if the overall magnitude and direction are the same. If the x and y and z components are all the same, that's just another way of saying that the magnitude and direction must be the same. Because the x and y and z components not only give you the overall magnitude of the vector, but because x, y, and z are directions, when you look at the magnitudes of those components, they give you the direction of the vector also. So if the x and y and z components are all the same, then the magnitude and direction of the vectors must be the same, and therefore the vectors are equal. Okay. Um, Vector components allow us to find sums and differences without graphing. That is very handy because I'm going to move the camera a little closer just to try to make the writing a little bit bigger for you to see it. um, the vector components, the fact that vector components or using vector components allows us to add and subtract vectors without graphing is very useful because, as I mentioned in class, if you're going to get accurate results by adding and subtracting vectors graphically, you have to be very, very careful in doing everything. You have to be very careful with measuring the magnitudes of the vectors. You have to be careful measuring the direction of the vectors. You're going to need a ruler and marked off very finely in millimeters at least. And you're going to need a protractor so you can measure the directions really well. And using the X and Y components eliminates all of that. You don't have to do a graph at all. Although, as I often said, it's still not a bad idea to do a little sketch of any given situation because that gives you an idea of what's going on. But still, that means that you can add and subtract and get an accurate answer without having to do any graphing and without having to be extremely careful in your graphing either. And so that's what I mean when I say analytical methods are usually more accurate. If the resultant vector is the sum of vectors A and B, then all you have to do is take vector A and vector B and add up their X and Y and Z components. So you add up the X components, multiply them by the unit vector in the X direction, add up the Y components, multiply them by the unit vector in the Y direction, add up the Z components, multiply them by the unit vector in the Z direction. Okay, so, and you can also independently write the resultant vector as the magnitude of vector r in the x direction times the unit vector in the x direction, and then do the same for the y direction and the z direction. So what that means is when you're adding vectors together, you could say that the x component of the resultant vector is ax plus bx, and same idea for the y and z directions. Ry, that is the y component of the resultant vector, will be ay plus by, and the z component of the resultant vector will be az plus bz. This makes it really easy to sum up a large number of vectors. With the graphical approach, it's pretty easy. I mean, well, maybe not easy, but not too much trouble to do 2 or maybe 3 vectors. But once you go beyond that, it gets to be kind of a nightmare trying to graph them all, accurately. But with using the components, you can sum up any number of vectors you want, and it's really not all that difficult. Okay, on page 70, there is an equation that can be a little confusing to look at. And so let me find it in the book and show it to you. What it means is essentially what I've done here. If you want the x component of a resultant vector, that is a vector that results from adding 2 or more other vectors, then what you do is you just add up the x components. In this case, we were adding 2 vectors a and b, so the x component of the resultant vector is the x component of a plus the x component of b. If we had other vectors, c and d and e and so on, then you would just add in those x components also until you run out of vectors. Same with the y. We were only adding 2 vectors here, a and b, so the y component of the resultant was the y component of a plus the y component of b. But if you had vectors c and d and e and so on that you were trying to add in, you would just add in those y components also for the y component of the result. And the same for the z direction. This equation 225 on page 70, that's essentially what this means. They go into the formal mathematical notation, meaning that the x component of the sum of the vectors is the summation of the x components of the individual vectors. And that's just the same thing that I was saying before. Only this looks a lot more complicated. So just don't let it fool you. It's a lot easier than it looks. Okay, and so that's what I was saying here. What it means is for the x component of the total vector or the resultant, you just add up all the x components of the individual vectors. For the y component of the resultant or sum vector, you just add up all the y components of the individual vectors. And for the z component of the sum vector or the resultant, then you just add up all the z components of the individual vectors. And it works the same way with subtractions. If you have vector A minus vector B, then the x component of the difference, which you would probably want to call D rather than R, would just be AX minus BX. And the y component of the difference would be AY minus BY, and so on. And you can do that. You can do it even if there's a combination of adding and subtracting. If well, it's getting more complicated now, but you can even combine adding and subtracting together. Okay, if you have 3 displacement vectors in a plane, this is an example 2.9. In a plane is another way of saying two-dimensional, x and y coordinates only. The 3 displacement vectors A and B and C in figure 213, way back on page 55, this book has an annoying habit of sending you back 10 or 15 or 20 pages to find a figure, and it doesn't tell you what page they're on either, so that's a real pain in the butt. But anyway, figure 213 was on page 55. You have vector A, which is at an angle with the y-axis, or sorry, the x-axis of 35 degrees and a magnitude of 10 centimeters. You have vector B, which has a magnitude of 7 centimeters, and it's at an angle of negative 110 degrees to the x-axis. And you have vector C with a magnitude of 8 centimeters, and it's at at an angle of 20, or wait a minute, is that 30 degrees? Can't read my own handwriting now. I believe it's 30 degrees with respect to the x-axis. Okay, so you can what it wants you to do is resolve the vectors into their scalar components and find these 3 things. The resultant, that is the sum of those 3 vectors, the difference between A and B, so vector A minus vector B, and vector S, which is going to be vector A minus 3 times vector B plus vector C. And the first one, that third one might look pretty difficult, but it's actually not all that difficult because we're doing it with components. Okay, what we've got is a magnitude and an angle for these 3 vectors. And so if you're looking for the y component of any given vector, or sorry, the x component of any given vector, it's the magnitude times the cosine of the angle. If you're looking for the y component of any given vector, then that's just the magnitude of the vector times the sine of the angle. And so what that means is that if you're looking for the x component of vector A, that's going to be A cosine alpha, which is what they called the angle for vector A. And that's going to be 10 centimeters times cosine 35. That's 10 centimeters. Cosine of 35 is 0.819 something, something, something onto infinity. And that comes out within a reasonable number of significant figures to 8.19 centimeters. So that's the x component of vector A. The y component of vector A will be the magnitude of vector A times the sine of angle alpha. So that's going to be 10 centimeters times the sine of 35, which comes out to 5.74. And the units are centimeters because the magnitude of A was in units of centimeters. The x component for vector B will be the magnitude of vector B times the cosine of beta. This right here is the lowercase Greek letter beta. Looks like a B, but well, because the Romans stole it from the Greeks, as they did most cultural attributes. And so our letter B, actually the capital letter beta is exactly like our capital B. The lowercase beta looks a little bit different, so they use that for the angle for vector B. The magnitude was 7 centimeters, and that's times the cosine of the angle. The angle was given as negative 110 degrees. Because they chose to go around clockwise from the x-axis to find that angle, you could also have used an angle of positive 250, which is what you get if you went counterclockwise around from the x-axis, and you would get the same result, because the cosine of 250 degrees is the same as the cosine of negative 110, which it should be because they're actually the same angle. And you end up with negative 2.39 centimeters as the x component for vector B. The y component is going to be b sine angle beta. And so 7 centimeters times the sine of negative 110, or positive 250 if you prefer, is negative 6.58 centimeters. And for vector C, the x component is going to be c cosine. That little thing there, it looks kind of like an R the way I've drawn it here. It's actually a lowercase letter of gamma in the Greek alphabet. They use that as the angle for C because, well, I guess for one thing, the Greek alphabet doesn't have a C, but gamma is in fact the third letter of the Greek alphabet. So you got alpha, beta, gamma. And so that's why they use gamma for C as the angle for C. Let's see. The magnitude of vector C was 8 centimeters, and the angle was indeed 30 degrees. And so it's 8 centimeters times cosine 30, and you get 6.93 centimeters as the x component for vector C. And the y component for vector C is c times sine of gamma, gamma being 30 degrees. And you end up with 4 centimeters exactly as the y component of vector C. So the first thing the question this is what you have to do before you can actually answer the question. For vector, so part A was, what is the resultant? A plus B plus C. What happens if you add up all of those vectors? Well, the resultant will be Rx, that is the x component of the resultant vector, times the unit vector in the x direction, plus Ry, and I don't know how I missed this. Plus the y component of the resultant times the unit vector in the y direction, plus, and forget about those that parenthesis there, plus the z component of the resultant times the unit vector in the z direction. All right, so Rx, that is the x component of the resultant, is just going to be all of the sorry, no, it's I'm getting ahead of myself. There's not 3 dimensions here. These were 2-dimensional, weren't they? Okay, so never mind, back to the original. All right, so Rx is the x component of the resultant vector is just going to be the x component of A plus the x component of B plus the x component of C. So all you have to do is look up at those numbers up here and take this plus this plus this. And you end up with 12.73 centimeters. The y component for the resultant will be the y component of vector A plus the y component of vector V plus the y component of vector C. So you just take this plus this plus this, and you get 3.16 centimeters. So that means the resultant will be 12.73 times I plus 3.16 times J centimeters. And that is the resultant of adding those 3 vectors together. Okay, the difference of vector A minus vector B will be a similar idea, only you're subtracting instead of adding. And we're only subtracting A minus B, and C is not involved in this part at all. So the difference vector is going to be the x component of the difference vector times the unit vector in the x direction plus the y component of the unit of the difference vector times the unit vector in the y direction. So the x component is just going to be the x component for vector A minus the x component for vector B, which is going to be, whoops, it's off the screen, this minus this. You can see 8.19 minus negative 2.39 is 10.58 centimeters. The y component for the difference is just going to be the, okay, I did make a mistake on this one. The y component for A minus the y component for vector B, and that's going to be 5.74 minus negative 6.58, and that's 12.32. So the difference vector is just going to be 10.58i plus 12.32j. Even though it was vector A minus vector B, you end up with both components being positive because the components of the vector you were subtracting were negative. And so you end up with everything positive. A little bit more difficult, but not too bad, is this next part, C. Well, we got vector S is equal to vector A minus 3 times vector B plus vector C. You find the components for this vector S the same way you did before. The vector S is going to be the x component of vector S times I plus the y component of vector S times j. So the x component of S is going to be the x component of A minus 3 times the x component of B plus the x component of C. So this is 8.19 minus 3 times negative 2.39. That's negative 2.39 plus 6.93. And that gives you 22.29 centimeters. The y component for vector S will be the y component for vector A minus 3 times the y component for vector B plus the y component for vector C. So that's 5.74 minus 3 times negative 6.58 plus 4.00 even, and that gives you 29.48 centimeters. So these are the x and y components of the vector S, and so vector S is just 22.29 times I plus 29.48 times unit vector j, and that's in units of centimeters. Okay. Okay, to continue that example, you might want to know what are the magnitude and directions of the resultant vector or the difference vector or the vector S that result from these operations. So remember, the resultant vector is just the total of A plus B plus C. If you want to know the magnitude of the vector, we've got the equation for the vector in terms of the unit vectors I and j. For the magnitude of the vector, again, you just treat the vector as if it's the hypotenuse of a right triangle. And so the magnitude of the vector should be the x component squared, the square root rather, of the x component squared plus the y component squared. And that's 12.73 squared plus 3.16 squared, the square root of that, which is 13.12 centimeters. For the direction of the resultant vector, the angle should be just inverse tangent, that is the angle whose tangent is the y component over the x component. So that's 3.16 over 12.73. And that gives you an angle of 13.94. So the resultant vector itself has a magnitude of 13.12 centimeters, and it's pointing in a direction or at an angle of 13.94 degrees from the x-axis. Okay, the difference, that is vector A minus vector B, the magnitude of that vector would be the, there it is, the square root of the x component squared plus the y component squared. So that's 10.58 squared plus 12.32 squared, the square root of that. And I never wrote down what that was equal to, but anyway, when you take the square root of it, it comes out to 16.23 centimeters. So that's the magnitude of the difference vector. And the direction of the difference vector, that is the angle of the difference vector, would be inverse tangent of the y component over the x component. So that's 12.32 over 10.58. When you take the inverse tangent of it, you get 49.35 degrees. So 49.35, probably be a little steeper than that. So it would probably look something like that, of the length of the arrow being 16.323 centimeters. In A, it would have made a very shallow angle of, well, about 14 degrees, and the magnitude would have been 13.12 centimeters. For S, we had to go through all this rigmarole to find out what S was, but once we have the x and y components for vector S, finding the magnitude and direction are pretty easy. So again, the magnitude of S itself should just be the x component squared plus the y component squared, take the square root of that. And so that's 22.29 squared plus 29.48 squared, take the square root, and you end up with 36.96 centimeters. The direction, again, is just inverse tangent of the y component over the x component. I kind of screwed up and originally put it the other way around. Anyway, it's 29.48 over 22.29, and the angle you get will be 52.91. So this one would be long because it's got a magnitude of 36.96 centimeters, and the angle would be 52.91 degrees. Something like that. Okay. All right. Well, I think that takes us to the end of the first segment of this lecture. So I'll be back in a moment with the second.